Questions. 10 kg of R134A fill a 1.348 meter cubes rigid container at an initial temperatures of negative 40 degrees Celsius. The container is then heated until the pressure is 200 kilopascal. Determine the initial pressure and also the final temperatures. In this question, they're asking for initial pressure, which is P1, and then the final temperatures, or we call it T2. Usually, for this type of question, I will suggest you to draw a diagram so easier for us to clearly see the information given. So this is going to be my state number 1, given that the mass is actually 10 kilograms. And then we have a volume of 1.348 meter to power of 3, and then temperatures of negative 40 degrees Celsius. And then it was gone through a process or a heating process until it reached a state number 2 or a final state, given that the pressure in the final state was actually 200 kilopascal. So in this question, the working fluids used are actually R134 refrigerants. Before this, during our lectures, we did a try to attempt couple of questions for which the working fluids are water. And then for water, you should remember by now, we can determine the properties by using a steam table, which is table A4 and A5 for the saturated liquid vapor, or we can use table A6, which is for superheated. If we take a look at this question, you should notice that for the state number 2 or final state here, we only have one properties. In order for us to use the steam table, we should have at least 2 different properties. In this case, we have the pressure, only pressure, but then we cannot really determine what are the properties in the state 2 here because of only one information or one properties is given. Because for the pressure of 200 kilopascal, it can be either in superheated, or sometimes it can also appear in the form of saturated liquid vapor. In this case, we need to have minimum of 2 different properties. So for this case, I'm going to start with state 1. Yeah? So for the state 1 here, I have a mass and a volume. By using these 2 information, I should be able to calculate for specific volume. From the formulas, I do know that specific volume was actually equals to volume divided by mass. And then I have a volume of 1.348 meter to power of 3 divided by mass, which is 10 kilogram. Then I should be able to calculate for specific volume, which is 0.1348 meter to power of 3 per kg. So now I have 2 different information. I do have specific volume, I do have temperatures. Since I already have 2 different properties, therefore I can determine other properties by using a steam table. So for this video, I'm going to show you, but then on the subsequent video, I'm not going to show you how do I get the values. Yeah. So this is the steam table. As I said before, previous example, we use a water. Therefore, we can use table A4 to A6 in order for us to find the properties of water. But then for this question, they give me the working fluids, actually refrigerants 134. Therefore, I have to use table A11, A12 and also A13 in order for me to get the other properties. So I'm going to scroll down to table A11. So see, saturated refrigerants R134A. Given in the question, the temperature was negative 40 degrees Celsius. Temperature at the state 1 was negative 40 degrees Celsius. And from my calculation, I do know that my specific volume was actually equal to 0.1348 meter cubes per kg. By taking a look at this information, I do have saturated liquid or VF equals to 0.0007053, and then I have saturated vapor with the value of 0.36064. But then I do notice that my specific volume was actually located in between these two values, in between VF and also my VG. Therefore, I do know that my state 1 here was actually in the phase of saturated liquid vapor. So going back to here, I can conclude that state 1 here was actually in the saturated liquid vapor phase. Why? Because my V, which is my V1 here, was actually located in between saturated liquid and also saturated vapor. How can I can come to this conclusion? You have to refer back to my previous video, because if you still remember that, if I'm going to draw my temperatures versus specific volume, I'm going to get something like this. So this is my VF, and then this is my VG. And then if my V, my value of V was somewhere around here, therefore most probably my state 1 was located somewhere around between these 2 points. So let's say it was located here, therefore this is my V1. So what happened if my V1 was actually bigger than my VG? So meaning that my V1 was located somewhere around here, which is bigger than VG. Therefore, I can say that it was actually located in the superheated region. So this is how I come to the conclusions that my state 1 was actually in the saturated liquid vapor phase. Alright, so state 1 was actually located in saturated liquid vapor phase. So from that, what I can do here is actually I can solve it. So my pressure at the state 1, P1, was actually equals to P1 or P set at negative 40 degrees Celsius, which is the value of, so I have to scroll back to the answer here, yeah. So because it was located in the saturated liquid, therefore my pressure for the state 1 is going to be, hold on, yeah, 51.25 degrees Celsius. So I can say that my pressure was actually equals to 51.25 degrees Celsius. So which is the correct answer. And then now I have to determine what is my final temperatures. So now I have to move to the state number 2. State number 2 here, I only have a pressure which is 200 kilopascal. But then in the question over here, it does mention that the container are actually rigids. What does the rigid container means? Rigid container means the volume is going to be constant. Meaning that my volumes at the state 2 is actually equal to the volume at the state 1, which is equals to 1.348 meter to power of 3. What is the opposite of rigid container? So the opposite of rigid container will be my piston cylinder. So this is my piston cylinder, but then if you notice that the piston here can move up or sometimes can also move down, meaning that the volume here is not going to be constant because the volume can be changed by moving up my piston over here or moving down the piston. If you're moving down the piston over here, the volume is going to be reduced, but then if you're going to move up the piston over here to up, and then the volume is going to be increased. But then in this case, the question does mentions that the container is a rigid container, therefore the volume is going to be constant. But then, as we learned in the chapter number 3, this is actually what we call a closed system. And then for the closed system, there's no mass flowing into or out of the system here. Therefore, the mass over here, M2, is going to be the same as mass at the state 1, which is equals to 10 kg. Therefore, my specific volume of the state 2 was actually equals to the specific volume of the state 1, which is equal to 0.1348 meter to power of 3 per kg. So now I already have 2 information instead of 1. Before this, I only have a pressure, but then by knowing only 1 properties, I cannot really use the steam table. But now I already have 2 information. So now I have pressure at the state 2 equals to 200 kilopascal, and then I have a specific volume at the state 2 equals to 0.1348 meter cubes per kg. So by knowing these two, I can use my steam table. So now I'm going to move into the steam table, which is table A11, A12, or A13. So here, if you notice that for the table A11 here is a temperatures table, meaning that the temperatures is varies. But then in this case, I only have pressure. Therefore, I have to use table A12 because A12 here is a pressure table. So now my pressure was 200 kilopascal. So P2, 200 kilopascal. And then I have specific volume of 2 at the point 2 or at the state number 2. The specific volume was actually equal to 0.1348 meter cubes per kg. So I have to check over here, because I do have VF and also VG. But then from here, by comparing my data here, I do know that my V2 here is 0.13. But then for my VF here is actually equal to 0.099, which is smaller compared to this one. Therefore, my state 2 here is not going to be in the saturated liquid vapor, but then it has to be in the state of superheated steam. Because by comparing the value of V2, which is bigger than VG, therefore, it should be in the superheated region. And then for the superheated region here, if you notice that the pressure given here is megapascal, but then my pressure at the state 2 is 200 kilopascal. I need to convert to megapascal. So I have to divide by 1000, divided by 1000, then I'm going to get 0.2 megapascal. 0.2 megapascal it's here. See, the pressure of 0.2 megapascal. And then my specific volume was actually equals to 0.1348. I'm not going to get an exact value. So here, my value was V2 equals to 0.1348 from my previous calculation. So 0.1348 should be located somewhere around 0.1348. 0.1348. So it should be located somewhere around here. See, because my specific volume was actually 0.1348, but then it should be located in between 0.1320 and 0.1364. Should be located somewhere around here, which is in between temperatures of 60 and 70 degrees Celsius. So what I have to do here, I have to record here. So I have to do the interpolation. So I'm going to move it here. So I will say that I will start with something like this. Pressure equals to 200 kilopascal or 0.2 megapascal. And then, and then I'm going to draw a line over here. So now I have temperatures of 60 degrees Celsius. And then I also have temperatures which is unknown. And then I have temperatures of 70 degrees Celsius. And then from the table, I should note that for the temperatures of 60 degrees Celsius, my specific volume was actually equals to 0.13206. And then for the unknown temperatures, which I want, the specific volume was actually equals to V2, which is equal to 0.1348. And then for the temperatures of 70 degrees Celsius, my specific volume was actually equals to 0.13641. Oh gosh, hold on, yeah. 0.13641. So means that this is the value which I want, but then I don't have the temperatures. But then this value, these two value, was actually coming from the steam table. Therefore, what I can do here, let's say the temperatures, unknown temperatures was T2, was actually equals to X. So I will say that X minus 60, this one minus this one, over this one minus this one, 70 minus 60 was actually equal to this one, which is 0.1348, minus this one, 0.13206, divided by this one minus this one. So it's going to be 0.13641 divided by 0.13206. And then I'm going to solve for X. So solving for X, I should get the value of 66.3 degrees Celsius. So this is my answer. So this is what we call interpolation, because our exact value is somewhere around 60 and 70. So going back to the steam table over here, yeah, oops, should be around here. Yeah, see, so I do know that my value, which is 0.1348, was actually in between these two values, in between 0.13206 and 0.13641. So this is my value, but then I have to determine what is the temperatures, T2. So the temperature should be in between 60 and also 70, because I'm looking for temperatures. So once I calculate it, and then I got the value of 66.3 degrees Celsius, which is correct because the value should be in between 60 and 70. Let's say you suddenly, after you calculate, and then you found that your temperatures was 80, which is doesn't make sense, yeah, because the value here was actually in between this value. Therefore, your temperatures also should be in between. T2 should be in between 60 and also 70 degrees Celsius. So once you got a value of, let's say you got 50, so means that there's something wrong with your calculation. So yeah, this is how we solve for that type of question, yeah, because usually for the test or for the final, it's not going to be, okay, read from the steam table, what is the value? No, that one is going to be too easy. So you have to, sometimes we're going to have 3 different states, and then we have to find the value for each state. And then the basic rules for the to use the steam table here, you have to have minimum of 2 different properties. So if you only got one, just like the state 2 in the example 1 here, you cannot really solve it, because by only knowing one properties here, you cannot really determine the properties. Why? Because 200 degrees Celsius here can be either in the state of superheated, or sometimes it can also be in the form of saturated liquid. So you have to have minimum of 2. So usually when you got only one information, you have to try to work out for you to get another information or properties, so that you can solve for the question. So now I'm going to move to the second part of the questions. Yeah. First, let me erase everything first. So sometimes they give me the working fluid of refrigerant. Sometimes they use water. So the only difference is just to use a different table. So don't worry much about the working fluids. So now I'm going to move to the second part of the question. 100 kilogram of R134A at 200 kilopascal are contained in piston cylinder devices for which the volume is 12.322 meter cubes. The piston is now moved until the volume is half of its original sizes. This is done such that the pressure of the R134 does not change. Determine the initial and final temperatures. Also calculate the change in the total internal energy of refrigerant 134. So let us try to solve for this one. Yeah. Hold on. Do I have point? Give me 1 second for us to solve for this one. Okay. And again, usually for this type of question, usually what I do here, I will draw a diagrams. Yeah. So that easier for me to have a clear pictures of the question. So this is my state 1, or my initial state, given that the mass was actually equals to 100 kilogram, and then the pressure here was actually equals to 200 kilopascal, and then given that the volume is 12.322 meter cubes, V1 equals to 12.322 meter to power of 3. And then the piston now is moved until the volume is half. So that this is the process. Yeah. So now it's stated that my V2 was actually equals to half of the V1, for which I can say that my V2 equals to V1, which is 12.322 divided by 2 is going to be 6.1 61 meter cubes. So my V1 here is actually equal to 6.161 meter to power of 3. And then this is done such that the pressure of R134 doesn't change. Therefore, I can say that my P2 here is going to be the same as P1, which is 200 kilopascal. This one is just given in the questions. Yeah. So now, and again here, I do have, for the state 1 here, I only have one properties, which is pressure. The mass and the volume is not really a properties. Yeah. So now I have to use my specific volume at the state 1 here is actually equals to volume divided by mass. Volume is 12.322 divided by mass, which is 100 kg, is going to be 0.12322 meter to power of 3 per kg. So now I already have two different information, which is I have pressure equals to 200 kilopascal, and then I have specific volume of 0.12322 meter cubes per kg. So by knowing these two information, therefore I can obtain another properties, because in the question it does asking for the change in total internal energy, which is U2 minus U1. Internal energy represented by the symbol U2, and also they're asking for what is temperature state 1 and then what is the temperature of the state 2. So now I have pressure of 200 kilopascal and specific volume of 0.12322. So now I'm going to move to the table A11 because they are using refrigerants R134A. So now I cannot use the table A11 because this one is temperatures table. Therefore, I have to use the pressure because the pressure is given in the question. The pressure U given was actually equals to 200 kilopascal. That one it was extracted from the information given in the question. So I have P1 equals to 200 kilopascal. So most probably my information is located somewhere around here. And then I also do have the specific volume V1 equals to 0.12322. So if you notice that here, my V1 was actually much way bigger than this one because this one is just 0.099. 0.0 means that out of 100 is going to be 9. But then here, if multiplied by 100, it's going to be 12. Therefore, most probably my state 1 here is going to be superheated because my value of V1 here is way bigger than my VG, which is for 200 kilopascal. Therefore, I have to use superheated because most probably my state 1 here is located in the actually in the superheated region. So my pressure was actually equals to 200 kilopascal. 200 kilopascal to convert to, because they use here megapascal, to convert to megapascal, kilo to mega, I have to divide by 1000, so it's going to be 0.2 megapascal. So here, so the table here, I have to use most probably this table because the pressure given was 0.2 megapascal. And then my specific volume was actually 0.12322. See, lucky for me, I don't have to do interpolations just like example 1 because the value here is so exact value. See, 0.12322. Therefore, my temperatures, my T1 is going to be 40, and then if you remember that the question asking for the change of internal energy, which is U, and then the value of U1 is going to be 263.09. So now I can go back to my answer sheet. So here, so I can write here my temperatures at the state 1 was actually at 40 degrees Celsius, and then my U1 was actually equals to 263.09 kilojoule per kg. This one I just read it, yeah? But then if you notice that even if you are going to use the saturated table, saturated refrigerants table, which is table A11 or A12, you're still going to get the answer. But then that one is wrong because of the specific volume here for my state was actually bigger than specific volume for the saturated paper. So this is my first answer, and then now I have to solve for the state number 2. So for the state number 2 here, I do have volume here, and then the mass here is going to be the same as state 1. Why? Because this is a closed system. In chapter 3, as I said before, in chapter 3 we learn about the control volume and also closed system. And then obviously for the piston cylinder over here, there will be any mass flowing into or out of the system. Therefore, the mass inside the system here is going to be the same. Therefore, I can calculate for specific volume for the state number 2 here is actually equals to volume divided by mass. My volume equal to 6.161 divided by 100 is going to be 0.06161 meter to power of 3 per kg. So now I already have two information. I have a pressure equals to 200 kilopascal, and then I have specific volume, which is 0.06161 meter cube per kg. So by knowing these two information, I can use steam table. And again, I cannot use steam table for A4, A5, and A6 as I used during my our lectures, because here is stated clearly that it is for water. And then the question given, they are using the working fluid are actually refrigerants. Therefore, I have to use either table A11, A12, or A13. So now, I'm going to move to the A11 first. I have to scroll. A11 is a temperatures table. Therefore, the given information was a pressure table. Therefore, I have to use table A12. A12 and A11 is just the same, except that one is for the temperatures, another one will be pressure. In this case, the given information was pressure. So my pressure was actually 200 kilopascal. So, and then, to recap, from my calculation, I do know that my specific volume was actually equals to 0.61. Oh, no. 0. I already forget. 0.061. 0.06161. So now, by comparing to this one, I noticed that my specific volume for state 2 or V2 here was actually in between my VF and also my VG, see? Because my value is somewhere around here, 0.06161, which is much lower compared to 0.0999551. Therefore, my value should be in between this value. So, because it was in between, therefore, it was located at the saturated liquid. So, so let me rewrite here. How to rewrite? So now I have my VF was actually at 200 kilopascal. My VF was actually equals to 0.0007618. 0.0007618, and then my VG was actually equals to 0.099951, and then my V2 was actually equals to 0.06161. So here, because of my value here was actually located in the saturated liquid vapor, therefore I have to use this formula. V2 was actually equals to VF plus X VFG. Or I can, this one we have to remember, yeah, means that the specific volume at the state 2 was actually equals to VF multiplied with the X, which is quality, steam quality, multiplied by VFG. So if I'm going to rearrange here, I'm going to have X was actually equals to V2 minus VF divided by VFG. And then V2 minus VF equals to VFG is just equals to VG minus VF. And then I can solve for this one. So I can say that my V2 equals to 0.06161 minus VF, which is 0.000718 divided by VG, which is 0.099951 minus VF equals to 0.00718, and then I'm going to get X equals to 0.6135. So once I get the X here, I can calculate for the U. Why? Because my U2 was actually equals to UF plus X multiplied by UFG. So my UF, going back to the table, I should note that my UF for the saturated liquid, so here my UF was actually equals to 38.26, and then my UG was actually equals to 224.51, and then UFG here equals to 186.25, and then here if you notice that UFG here is just simply UF divided by, UG divided by UF, then you're going to get the UFG. Sometimes for the saturated for the specific volume, we don't have the VFG, but then it's just the same formulas, meaning that UFG is just a mixture. To get this one, UG minus with the UF. So now I'll be able to calculate for U for the state number 2. So where was my question? Okay, here. So from the steam table, I do know that my UF at 200 kilopascal, my UF equals to 38.26 kilojoule per kg, and then my UFG was actually equals to 100, is it 186.25 kilojoule per kg. Therefore I can use U2 equals to UF, which is 38.26, multiply with the plus X, which is steam quality, which is already calculated before. Where was it? Oh gosh, I erase it most probably. So X, so U2 equals to UF plus X multiplied by UFG. So X equals to 0.6135 multiplied by 186.25, and then I'm going to get the answer of 152.52 kilojoule per kg, and then delta U is just equals to U2 minus U1, then I'm going to get the answer. Yeah, this is two type of question, which is how we're going to apply it. But then for this example, they are using the refrigerants instead of using a water. Yeah? So I'll try to provide you with more videos on the refrigerants, most probably around another video on the refrigerant, and then another 2 videos for the water, so that we can learn on how to read the steam table correctly. Thank you.